You write a few lines of Python, hit run, and the screen outputs a perfectly structured essay or a block of functional code. It's easy to look at that output and assume there is a ghost in the machine, that modern AI models possess some kind of unexplainable emergent reasoning. But that reasoning is an illusion. An AI is an entirely deterministic system. Underneath the interface, it is strictly calculus and linear algebra, executed sequentially in Python. When we shatter the exterior, we don't find a digital brain. We find a highly structured, stacked hierarchy of mathematics. To understand exactly how this works, we have to start at the absolute bottom, translating human language into foundational math, and then scaling those equations into a functional neural network topology. From there, we will implement the specific transformer architecture that makes large language models possible, and optimize it using parameter-efficient fine-tuning so it can run on consumer hardware. Tracing this sequential stack from the ground up removes the mystery. It provides a rigorous, replicable blueprint for building an AI completely from scratch. The first engineering problem is translation. A computer cannot process the qualitative meaning of human text. It only processes numbers. Using linear algebra, we assign numerical values to vocabulary, plotting words as discrete coordinates in a high-dimensional vector space. Then, a matrix sweeps through, using multiplication to physically reposition those data points and generate an output. Naturally, the model's first attempt will be wrong. The mathematical distance between its initial prediction and the correct answer is called the error. To fix this, we need an optimization engine. This is where calculus takes over. By calculating partial derivatives, the system can determine the exact slope and direction of that error. Using gradient descent, the model steps down this slope, iteratively adjusting internal numbers until it hits the absolute bottom of the topological valley, representing the lowest possible error rate. This specific process, mathematical minimization, is the literal definition of machine learning. What we perceive as artificial intelligence is not cognitive reasoning. It is the automated minimization of error via gradient descent. Knowing the math is one thing. Executing it at scale requires a dedicated structure. A neural network topology is simply a structured framework designed to run millions of matrix multiplications simultaneously. Data flows through this framework in a single direction, a process known as the forward pass. Input data is multiplied by numeric weights until it reaches the end, outputting a prediction. The system then mathematically compares that final prediction against the ground truth to calculate the total error. To correct this error across the entire network, we use backpropagation. The calculated error derivative is sent backward through the system, mathematically updating the weights along the way. A neural network, therefore, is an engine built for two distinct functions: executing matrix multiplication forward and gradient descent backward. But this standard architecture has a severe limitation when dealing with human language. Because it processes data strictly in sequence, token by token, it inevitably loses the context of early words by the time it reaches the end of a long paragraph. The transformer architecture was developed specifically to bypass this bottleneck. Instead of analyzing words one at a time, a transformer processes the entire sequence in parallel. It achieves this parallel processing through a mathematical mechanism called self-attention. Self-attention instantly draws a mathematical link from every word in a sequence directly to every other word. The system assigns a numeric weight, heavily highlighting words that depend on each other while muting the rest. This allows the model to map the full semantic context of an entire document at once, without ever reading it from left to right. This specific capability is what made large language models viable at a global scale. Generative AI did not arise from a change to the foundational math. It was the topological shift to self-attention that finally solved the context problem. Modern transformers are massive. Their internal weight matrices contain billions of individual parameters. Attempting to run backpropagation across a matrix of that size places a crushing load on hardware. Standard full parameter training requires clusters of data center GPUs. If an individual engineer tries this on a standard machine, they will instantly run out of memory. We bypass this hardware restriction using low-rank adaptation, or LoRA. Through matrix decomposition, LoRA takes the massive target weight matrix and splits it into two dramatically smaller matrices. The original matrix freezes, so training only updates the two small matrices, reducing parameters by orders of magnitude. Engineers combine this with quantization, known as QLoRa, which further shrinks memory requirements by reducing the precision of the numbers from 16-bit down to 4-bit. By implementing LoRa, we preserve the model's core logic, while shrinking the computational demand from a massive server farm down to a single consumer graphics card. We now have a complete operational stack. At the base, linear algebra translates raw human language into numeric coordinates. Above that, calculus optimizes those numbers by navigating the error gradient. The transformer layer processes those optimized tokens in parallel, using self-attention to retain perfect semantic context. And finally, matrix decomposition ensures the entire structure is computationally light enough to train and deploy. There is no emergent consciousness at the top of this hierarchy. It is strictly an interlocking stack of deterministic engineering principles. With this blueprint in hand, you are no longer restricted to just writing prompts. You have the exact mathematical tools required to build and train your own generative model from the ground up.